This is Physics 102B, Chapter 17 homework, Part 1. Starting with number 35, we have a wire with the given length and radius. So to find the resistance, we use resistance equals rho, the resistivity times length divided by the area. It's a circular cross-section wire, so the area is pi r squared. So we have rho times length divided by pi r squared. Plug in those numbers, and you should get 8.75 times 10 to the negative fifth ohms. Number 36 asks about the temperature for different resistance changes. So first we use the resistivity equation. This equation is given to you in the book with rhos instead of the r's, but as I showed you in class, you can substitute the r's for rhos. Solve it for temperature, and you get this line here. Now, in the numerator, there's r over r naught, meaning final resistance over initial resistance. So for Part A asks about a resistance increase of 1%. So resistance is going to be 1.01 times initial resistance. So r over r naught is 1.01. And when you plug into this temperature formula, you get this fraction right here becomes 2.56 degrees Celsius, but then you're adding it to 20 degrees Celsius. So a final temperature of 22.56 degrees Celsius. Part B asks about a 10% increase. So the ratio of r over r naught is 1.10. And when you plug in the numbers to temperature, you get a final temperature of 45.64 degrees Celsius. Next is number 38. Number 38 asks about how many electrons pass a given point. So we start with the definition of current being Q over T. So Q is I times T. Now Q is the charge. If we want to know about the number of electrons for a given charge, we can replace charge with number of electrons times the charge of each electron. So I've replaced Q with N, which is what we're solving for, times E. Sorry about that. Equals IT. And we solve for N. It's current times time over the elementary charge. And so you plug in those numbers and you should get 6.2 times 10 to the fifth electrons. Number 42. There's the same temperature equation that we got in number 36. So I came up with a shortcut way of doing this, an easy way using some algebra. We have r over r naught. The thing is, r and r naught are not given directly in the problem. So here in the green ink, I wrote, what is r over r naught? So we can use the Ohm's law, that current equals V over R. So R is V over I, and R naught is V over I naught. Now you don't need a V and a V naught separately because voltage stays constant. So we can say that R over R naught is V over I times I naught over V. That's the R times the reciprocal of R naught. The V's will divide out, and what we're left with is I naught over I, which is good because that's what the problem is. That's the information given in the problem, I naught and I. So now our temperature equation becomes, instead of R over R naught, we have I naught over I minus 1 over alpha plus T naught. plug in those values, and we get an answer of 308 degrees Celsius. I'd originally assigned problem number 43, but I'd like to skip that one. It's a bit more convoluted than I care for. So let's go on to number 52. When resistors are arranged in series, the equivalent resistance is their sum. So 34 ohms plus 45 ohms is 79 ohms. Part B, the current is the voltage divided by that equivalent resistance. 75 volts divided by the 79 ohms, or I'm sorry, 7.5 volts divided by 79 ohms, and that gives us 95 milliamperes. Number 53 involves two resistors arranged in parallel, and for this you use the relationship that the reciprocal of equivalent resistance is the sum of the reciprocals of the resistances. So 1 over 250 plus 1 over 370. So we have 1 over the equivalent resistance is this small number, 0.0067. Take the reciprocal of that to get the equivalent resistance, and we get 149.2 ohms. Part B, we use Ohm's law. Take the voltage divided by that equivalent resistance, and we get 0.080 amperes. Now the question asks, what about the current through each resistor? And as I'm filming this in spring 2013, I did not cover this in class, and my students aren't responsible for it. But here it is anyway. Each resistor in this setup has the 12 volt difference across it, so we use Ohm's law to find the current over each resistor. So in the first case it's 12 volts over 250 ohms, and in the second case it's 12 volts over 370 ohms. You get those resistances 0.048 and 0.032, and notice that the original current that we found in part B, 0.08 amperes through the battery, that's divided up between these resistors. The higher resistance got less current through it, but they both add up to be 0.08. And that's the end of part 1 for chapter 17.